So this idea that you can use induction on lists is a pretty powerful idea, but it's not totally obvious to you know, when you get started. So let's try another example, and let's see if this makes it any more clear. Okay, so I'm going to start with a definition that's also in the programming assignment, and here we're looking for membership. Okay, so what this actually corresponds to is that member ES is basically the same as what we've been saying, E belongs to S. Okay, so that's what that means. Now, how does it work? Well, the first thing we ask is S a const P? Meaning, is it a non-empty list? Okay, so this is the then part, and here is the else. Okay, so if it isn't a non-empty list, that means that it must be an empty list, then the answer is nil. That's false, right? Because there's nothing in the empty list or set. Okay, now otherwise there are two possibilities, right? So what we have is a list. So S is equal to S1 and S2 up to Sn, for example, right? So that's what happens in this section. Okay, so we think of that as S1 const with S2 up to S sub n, right? And I'm mixing notations here. That vertical bar is from Prolog, but it sure makes life easy. Okay, so there's two ways that the element E could be in S. The first way is if E happens to be the first element of S. That means S1, right? So is E equal to that? That's the question. If E is equal to that, then absolutely yes. Yeah, so we return T. Absolutely yes, E is a member of S. Otherwise, well, if that's false, then it must be the case that E has to be in here. Okay, and so we have E is a member of the rest of S. That's what the answer is. If E is a member of the rest of S, then yes, E is actually a member of S. If not, then actually no, E is not a member of S, right? So we can just return that. Okay, now here are three equations that kind of capture that. Okay, so we have E is a member of nil. No, that's false. E is a member of const AL. Well, that's true if E is equal to A. Otherwise, E is a member of const AL if E is a member of L, and if E is not equal to A. Okay, so notice that I have three equations here, and over here, what I have are two ifs, right? And the purpose of the if is just to tell me I am in equation 1, equation 2, equation 3, and then the actual result is the right-hand side. So you see nil, true, and member E of L, which is the rest of the list S. Okay, so that's another function that we can work with. Okay, so here's a theorem that we can say. Okay. Suppose that I have a list which happens to be a list of natural numbers. So LONP, right? That's what that means. Okay, L is a list of natural numbers, and also suppose that E is a member of that list. Okay, then I can conclude that E is a natural number. Okay, nice and straightforward, right? If E belongs to a list of natural numbers, then of course E has to be a natural number. So let's prove that again using induction. Okay, so we're using induction on lists, and the list that I'm going to use induction on is L. Notice that it's kind of the only list that appears here, right? L, right? That's their only list. Okay, when we did the union before, we actually could have chosen either S1 or S2. If you want, go ahead and try doing that with S2. I think you'll find it's a bit harder. You actually need some extra lemmas ahead of time, but they're actually not that hard to prove. Okay, but anyway, let's take care of this. So let's suppose that the list is equal to nil. Okay, so what we have is that nil is a lonp, and E is a member of nil, and that's supposed to prove that E is a natural number. Okay, now the problem is that E can never be a member of nil, because actually if you look at the definition of member, it starts out by saying if L is not a non-empty list, right? Then the answer is false. Okay, so this actually just happens because definition of member. Okay, and once we get this false here, then the proof is finished, because basically that means that the hypothesis is false, and of course that implies anything, right? So we just get true. Okay, so the reason that the base case works really easily, okay, is that nothing can ever be a member of the empty list. Okay, so that's our base case, and that's perfect. Okay. All right. Now let's think about the induction step. Okay. So what do we have in the induction step? Well, what we have is that L is somehow equal to the cons of some element A and some other list, right? Which we also call L, but that's just, probably should call it L2 or something to be more clear. Anyway, so let's go ahead and instantiate our theorem that we're trying to prove. So what we have is that cons L is a list of natural numbers, and that E is a member of that list, cons L, and then we should conclude that E is a natural P. Okay. All right. So now where do we go from there? We say that A is a natural P and lonp P of L, right? This is actually just the definition of P, right? And the term that I'm looking at is lonp P of cons L. Okay. So by opening that up using the definition of lonp P, we get this. We now know that A is a natural number and that L is a list of natural numbers. Okay. Well, now let's look at the definition of member, right? And we get this, and this is just definition of member. And in the definition of member, when the list is not an empty list, then there's actually two ways, because there's two equations. There's two ways for E to be a member of that list. Either E is equal to the first element, or E is a member of the remainder of the list, right? So that's our or here, right? There's two ways for that to be true. Okay, so now let's break that, okay? Because you see there are two cases, so let's kind of think in terms of case 1 and case 2. So here is case 1, okay? And case 1 is when E is equal to A, and then here is case 2, okay? Which is when E is not equal to A, but E is actually a member of L, right? So this is case 2, and this is case 1. Okay. Now, case 1 is very easy because case 1, the hypothesis is that A is a natural number, and the conclusion is that E is a natural number. But the hypothesis also tells us that A is equal to E. So, of course, E is a natural number. So this is obvious, right? You know, the case 1 is just true. But now let's look at case 2. And case 2 tells us that A is a natural number, L is a list of naturals, and E is a member of L. Okay. Well, if we simply ignore A is a natural number and just look at this, right? We get that from the induction hypothesis, because the induction hypothesis tells us that if L is a lonp P and E is a member of L, then E is a nat P. Okay, that's what the induction hypothesis says. So technically, this isn't a one step. That's why I didn't use an equal. I used dots and eventually. But with just propositional reasoning and the induction hypothesis, we can reduce that also to true. Okay. Well, then we're done, right? And so we now proved that if L is a list of natural numbers and E is a member of L, then E has to be a natural number. Again, the important thing is not the theorem. The important thing is this idea that if you have a recursively defined type, then you can write functions that process that type, such as member. Okay, you can write functions that process that type, and they're naturally going to be recursive functions. Okay, following the same kind of pattern as the inductive definition. And then when you want to prove some properties of that function, then again, very naturally, you'll end up using induction and an induction proof. And that induction proof mimics the inductive definition of the type. So we call it structural induction. The reason we call it structural induction is because it's working down the structure, of some kind of strange type, right? Here we're walking down the structure of a list.